Whenever we are talking about electron and holes, we would always have them on equal number. And that's the relationship P equals N, right? Number of holes equals number of electrons. So N will be always concentration of electrons, P will be always concentration of holes. It may have a subscript with it, like here we have written Ni. So I here stands for intrinsic. Anybody remembers what was the Ni for silicon? This is a number you have to remember forever. Intrinsic value of charge carriers in silicon. It would be 1.5 times 10 raised to power 10 electrons per centimeter cube. We'll be always talking about a volume when we talk about charge carriers. So now when you write Ni, which means it can be number of electrons or number of holes, whatever is the situation, but we'll write Ni only instead of writing Pi as well. But Pi is also a valid way of writing those things. When we write about intrinsic charge carriers, we know they're the same number, but when we dope it, then we are changing one of those. Either we are changing the electron concentration or hole concentration. So this is what happens. And it says, I underlined, in addition to the intrinsic carrier concentration, then we add carriers from outside. Then we add dopants. That process is called doping. And what it does is it varies the conductivity of semiconductor. Very, very small amount can dramatically change the conductivity of semiconductor, silicon, like we are saying. Now, if we are using N-type semiconductor, electron hole concentration will no more be Ni. That will become N naught. We will denote it with N naught. But the hole concentration will stay Ni. Now, you can say, okay, hole concentration was P, but I say the hole concentration would stay Ni because in the previous slide we just said N is equal to P is equal to Ni for intrinsic materials. But depending on what kind of doping we are doing, it will be either N naught now for the electrons if the dopant is electron, or P naught if the dopant is holes. So just basic notations of how we will identify what kind of carrier concentration we are talking about whenever we are dealing with calculating or finding out exact numbers of the carrier concentrations. Now, this word carrier concentrations I'll be talking a whole lot about it, right? So in the situation of the device, if it's an N-type device and I say carrier concentration, you know I'm talking about electrons, right? Because the N-type, the whole concentration is intrinsic level, that would not change. Does it make sense? Why? It's simple concept, but we need to know because when we keep on building on this, we need to understand the terminology. So now in intrinsic material, if you dope it with a, what kind of material is this? P-type, because it is contributing a hole, right? Aluminum. What are the groups that are P-type dopants?
Group 5.
Group 5 has one extra electron. That's an extra electron type.
Oh, so group 3.
Group 3, yeah. So group 3 is one which is one electron short, which means it is bringing an empty space. It's bringing a hole to the party. We call this acceptor because it has an empty space. It can accept electrons. Now, if I take group 5, it will come with an extra electron, right? So that is being added to the pool of electrons there. This comes from group 5, and this contributes. So antimony is an example of group 5. Now, once we have done that, we would have, of course, the electrons that are excited intrinsically and electrons that can be easily excited to be in the conduction band, which are contributed by dopants. So this in now the electrons that are contributed by the dopants, for example, in n-type, they are not adding any holes because they are just contributing from outside. They are not being added to conduction band because they're jumping from valence band. Understand? So hole concentration will stay the same as it was before, but only for n-type, only the electron concentration will dramatically change. When electrons are dramatically high, your conductivity will change dramatically, which means now from a semiconductor material which was almost behaving like an insulator, now you got a conductor out of it. Now, if you do this with holes, when you contribute materials which are acceptor, group 3, they would now create many empty spaces. The holes are many, many more. So basically those empty states which lack electrons. Now the whole current will start moving much faster. And these holes are given positive charge. The current flow is same. Now, when I say current change, current for the movement of electrons, we always take the current opposite to the movement of electrons. If electrons are going this way, we denote the current to be going the other way. But holes, if they're going this way, their current is also taken in the same way. We'll revisit that later in this chapter. But for now, we just say, okay, both have their own ways of how they change the conductivity. We have been writing this thing E Fermi many places, aligned somewhere in the middle. Well, that's a energy level which basically characterize a, every solid. We use that energy level called Fermi level to say, okay, and we'll not go into the mathematics of that, but it's been proven that above that energy level, there is higher probability to have an electron. Below that energy level, there is less probability to have an electron. At 0 degree Kelvin, we say above that they are filled and below that they are not filled. For semiconductor, for intrinsic material, we put the Fermi level right in the middle. So we say, okay, there's equal probability to have an electron and a hole, right? Because they are the same number. But that Fermi level would change if it's n-type or p-type. Now, revisiting the silicon structure, remember silicon had diamond structure. So this is now the 3D unit cell. And when we add a dopant like blue ball that is shown here, that will be contributing extra electron now. Now that electron can, depending on what is the plane and which direction the current is flowing, with wave vector, propagation constant, so they will then define whichever way it goes and how it would propagate. So essentially, when we do doping, we replace a silicon atom in that lattice structure and introduce that dopant, like it's shown in this picture. So to recap, extrinsic materials, they are two types, n-type or p-type. Group 5 are n-type. We call them donors because they donate electrons to the system. And they are antimony, arsenic, phosphorus. P-type are group 3 because they have empty spaces. They accept those electrons in their spaces. We call them acceptor as well. And they are generally boron, gallium, indium. So just to look at specific examples again, here we are showing antimony, right, which is replacing one silicon atom and then have an extra electron, which is being pulled around. And when we do that, we push the Fermi level. If we are doing N-type, we push the Fermi level close to conduction band, which means now there are many, many more electrons. So the probability of having more electron dramatically has gone up because Fermi level is close to conduction band. For now, this is what I want to remember, that if Fermi level is close to conduction band, it's an N-type, many more electrons. But if the Fermi level is close to valence band, it's P-type, many more holes in there. So the level of Fermi level, looking at band diagram, tells us what kind of material would that be. So now in a p-type material, the Fermi level would be drawn closer to valence band. So in band gaps, in a band diagram, the levels, the values, the location of Fermi level tells us right away what kind of material are we dealing with in whatever device we are looking at. All right. Now, when you have electrons and holes, how do they flow? So we justify holes as a charge because there is a one electron less. But essentially, it is again movement of electrons, right? But we only look at holes. Whichever direction holes go, we call that to be the direction of the current. Whichever direction electrons go, we take the opposite of that. Now, how big of a effect the the doping has, this is just an example. I took copied this line from the book, that if we dope silicon with this many arsenic atoms, it itself has 10 raised to power 10, to be precise, 1.5 times 10 raised to power 10 for silicon. And if you add this many arsenic atoms, the resistivity goes from 100,000 ohm centimeter to just 5 ohm centimeter. So you can see there is 5-order decrease in the resistivity of silicon. So do you see the dramatic change that you would have just by introducing 10 raised per 15 arsenic atoms in silicon? Now, this dopant is just replacing silicon atoms in the whole crystalline structure. It does not disturb the crystalline structure itself. So the device physical integrity stays the same, but electrical and electronic properties change dramatically. Now, at this stage, there are a few things which we would readily know whenever we look at it is in an N-type material, we distinguish electrons, we call them majority carriers. When you say majority carrier, which means you're talking about the high number of charge carriers. In those cases, we call holes as minority carriers. But if you talk about p-type material, and if you say, oh, majority carrier is doing this, we basically mean holes. In that case, electrons are minority carriers. We established this language because we don't want to deal with every time that N-type and p-type. We can generate general theory, and in that case, we can say, oh, majority carriers will do this and minority carriers will do that, right? But if you clearly specify we are talking about N-type, so you will then know, okay, majority carrier are electrons and minority carriers are holes. And the reason is that even if you have an N-type doping done, holes are still there, right? So we are still interested in knowing the minority carrier concentration because there will be always electron hole recombination happening, right? So electrons and holes will be continuously recombining as well. So we need to know how many of the minority carriers are there, right? Now, when we talk about the levels of energy that are introduced by doping, the overall change in the concentration is depicted by Fermi level, which is shown here as EF. A band diagram shows us level of conduction band, EC, basically energy level, valence band, level of valence band edge. Then if we are introducing acceptors, we know where are the levels of acceptors, energy levels. Then we know where are if we are doing N-type doping, we know where are the levels of energy which are introduced by donors, right? But then we have concern of overall energy, overall concentration of majority carriers. Now, their levels would be somewhere in the band gap, but we need to precisely know where they are because that will tell us exactly how many charge carriers are there. Now, if you're looking at these levels of uh, donor levels or acceptor levels they are introduced, they are very close to the respective bands. So, for example, the donor levels for from group 5, column 5, are about zero point zero 0.01 electron volts below the conduction band for germanium. And if we talk about the acceptor levels, they are also in the same order, very close to the valence band, zero point zero 0.01 volt. But their contribution to the number of charge carriers are much, much bigger and much, much more profound, have bigger impact. So hence, we write this Fermi level that tells us how many charge carriers of one type are there. But where does it come from?